Okay, so the flip side to talking about heat and how heat moves from one object to another is asking, how can we stop heat from flowing between objects? When we want to keep a mug of hot coffee hot, as I do every morning when I'm teaching this class, what can we do to slow down the flow of heat away from the coffee? What sets the limits on how well we can insulate that mug of coffee, or insulate ourselves from, a cold winter's day? Or for that matter, how does the Earth and the Earth's climate effectively regulate how it's insulated from the sun's incoming rays, right? So that's what we're going to talk about in this section. It turns out to be impossible to actually completely isolate any object so that it doesn't gain or lose any heat whatsoever. But we'll look in the following sections at each of those three mechanisms of heat transfer, of heat flow that we talked about in section 8.2. And we'll discuss both those mechanisms in more quantitative detail, and then we'll use that detail to help us understand how to slow down the flow of heat. A first point is that, in some sense, losing heat or losing energy to thermal energy is almost like an unavoidable waste. At least it's a waste from the perspective of, from our point of view, where we're trying to get things done, we're trying to do work. And so, for instance, the force that I'm putting into sliding a bookcase, I wish I could just apply a force, have the bookcase accelerate a little bit, and then just keep traveling to its destination. Instead, I have to constantly do work against frictional heating. Right? Similarly, we burn a lot of gas trying to drive our cars from point A to point B, and as we're cruising on the highways at high speeds, actually most of the energy from the gas we're burning is just going into, adding thermal heat to the air around us in the form of turbulent wakes and stuff like this. And indeed, anytime, heat is leaving an object that needs to stay at some temperature in order to function, like, for instance, every warm-blooded mammal, whose body temperature needs to be very carefully regulated for biological function, as that object is losing heat, you have to spend energy just to replace the heat that you lost in the first place. So for instance, for a human, you probably have a sense that we need at least in the ballpark of 2,000 food calories every day to function. That's not even including, if you're exercising a lot, this number goes up, anything like that. That's just basically how much food do you need to eat just to sit on a couch and relax, but still function. So 2,000 food calories per day, that's like 83 kilocalories every hour. And if I convert this from kilocalories to joules per second, that's like 96 watts. Okay, so our bodies are constantly acting like 100-watt space heaters, basically. And that's why if you have a bunch of people in a room together, that room can get uncomfortably warm pretty quickly, right? So, it turns out that the human body is much better at regulating how it releases heat into the environment than it is at regulating how much, thermal energy it has to generate in the first place. And so the body and the physiology of the body has all kinds of interesting tricks for, for instance, using evaporative cooling from generating extra sweat if it needs to maintain this temperature and the weather is hot, so on and so forth. Of course, the easiest way to maintain your temperature, especially in cold weather, is just to put on more clothing. And both that strategy and other strategies of thermal insulation are what we're about to talk about. So section 8.3.1, first let's talk about limiting thermal conduction. Seems like a good idea. Limiting thermal conduction. So in the last section, we learned that heat can flow through a material by conduction whenever one part of that material is hotter than another part of it, right? Or if an object is physically in contact with a hotter or colder other object, right? How fast does heat actually flow by this mechanism, though? And the answer to how fast does heat flow by conduction? How fast does heat flow by conduction? This depends, on a lot of things. First and foremost, it depends on the material itself, right? So, heat flows better through some materials than others. And this kind of property of how well heat flows through a material is sometimes called the thermal conductivity. Thermal conductivity is a measure of this. And it has units, SI units, of watts per meter per Kelvin. Watts per meter per Kelvin. Right, so how much thermal energy flows through a distance if the difference in temperature between two parts of a material, or between one object and another that it's physically touching, is a certain number of degrees Kelvin, right? And here are some typical numbers. So I have to write these down because otherwise I don't remember them. For instance, e.g., gold is about 310 watts per meter per Kelvin. So that's the thermal conductivity of gold. Steel, that's about 50 watts per meter Kelvin. What else do I have on this list? Window glass, about 0.8 watts per meter Kelvin. We're getting weirder. Human skin, 0.21 watts per meter per Kelvin. Wood, I think this is a number I looked up for oak, 0.17. Let me write that a little clearer, 17 watts per meter per Kelvin. And air, 0.025 watts per meter per Kelvin. Okay, so one of the things that you should notice is that different materials can have really an enormous range of how thermally conductive they are. And that goes even for objects that are kind of in the same category of material. So, gold and steel, those are both metals, and metals conduct heat very well. But even within the category of metals, there can be a big difference, almost an order of magnitude, in how well they conduct heat. And similarly, non-metallic substances also have, a big range, from less than a watt to barely 1/100th of a watt per meter per Kelvin. Okay, so how fast does heat flow by conduction? One part of that answer just has to do with, well, what is the material in the first place? What else does it depend on? B, it also depends on the difference in temperature, either between the different parts of the object or between the two objects that are in contact. And that you can kind of, again, get a clue from the fact that the units for conductivity are per meter per Kelvin. So the more different temperatures are, the more heat can flow, the faster heat flows. Right? Great. And so, for instance, if you're standing in your socks on a cold floor, if that floor is 10 degrees colder than you are versus 40 degrees colder than you are, the heat will flow 4 times as fast from you to the floor when there's that 4 times as big temperature difference between you and the object you're in contact with. Okay, so heat flow depends on material, it depends on difference in temperature, it depends on the area. So for instance, again, you're standing on the floor in your socks. If you start standing on one leg, there's only half as much area of contact between the objects at different temperatures, and so heat flows half as quickly. Half the area, half as quickly. Okay, that's great. The final thing it depends on is the separation between the two objects. So for instance, I'm standing in my socks on a floor. If I make the socks twice as thick, then that cuts the rate of heat flow by a factor of 2. So separation between hot and cold parts of the object or objects themselves, right? So if I put all of these factors together, the heat flow via conduction is like the thermal conductivity multiplied by the temperature difference, multiplied by the area of contact, or the area through which the heat is flowing, all divided by the separation. Okay, that's putting those 4 pieces together into this single equation. And in symbols, I might call this something like heat flow being equal to some thermal conductivity, and I'll just use the letter K, multiplied by a difference in temperature between the hot and the cold object, multiplied by the area through which the heat is flowing, all divided by some separation D. As you've probably noticed for a few chapters now, there's more physical concepts than there are letters, and so we have to start reusing letters or using Greek letters sometimes, and it's much more important to, in your mind, remember this kind of set of concepts. What is this equation actually linking together? Heat flow is being linked with thermal conductivity, temperature differences, areas, and separations, the particular symbols that I use to represent each of these concepts, those are just arbitrary. But there you go. This is how heat flows by conduction, and that helps us understand what limits we can place on how fast we lose heat by conduction. So for instance, if we're trying to pick up a hot frying pan, well, if we want to limit the heat flow, we could put in between our skin and the frying pan a substance which doesn't conduct heat very well, like the fibers in an oven mitt. We can make the oven mitt really thick, and we can limit the area of contact that we're actually working with. In that particular case, the temperature difference is like the thing we're not controlling. Our body temperature is our body temperature, and we've heated up the iron skillet to whatever temperature we need it to cook our food, but we can control these other things in this case. All right, what about strategies for limiting convective heat loss? Convective heat loss. The human body actually does a surprisingly good job of minimizing conductive heat loss by controlling the things that it can control. So for instance, skin has a pretty low thermal conductivity. Actually, fat also has a very low thermal conductivity. And so, we've got skin, we've got layers of fat underneath the skin, and that slows down the flow of heat from the core of our body to the outside air around us. So the body does a good job of optimizing this. It can't control the temperature it needs to be. That's set by, the limits of biological functions. And actually, the human body does a pretty good job of being a good shape so that it doesn't have lots of excess surface area. We've got arms and legs because we need to move through the world and we need to interact with objects. But otherwise, actually, the core of our body is a pretty compact volume, right? It's not like a super flat, extended sheet. The body is pretty compact. And so the body does a pretty good job of limiting conductive heat loss. And that's nice. That's very helpful, I suppose. But there's only so much you can do. Even by playing with these factors or evolving them so that they're as good as possible, the body is still going to conduct heat to the environment around us. That is, the human body will typically be warmer than the air it's in contact with, just about everywhere on Earth anyway. And so it will always lose heat to the air that's around it. Okay. Now, air itself is a very poor conductor of heat, which we know from this extremely low value of thermal conductivity relative to all of these other substances. And so actually, if you were staying perfectly still, you would only heat up a pretty thin layer of air next to you. Because air doesn't conduct heat very well, the body doesn't really heat up air far away. It really heats up the air molecules very close to your skin, right? So if you could get that air to stay still, then you really wouldn't lose nearly as much heat to conduction, right? Because the temperature of the air that's quite close to your body would be almost the same as the temperature of your body, right? And so this delta T would get pretty small, and you wouldn't lose very much heat to conduction. That would be amazing. The problem, as you know, is that warm air rises, right? Warm air is less dense than cold air, and so the buoyant force will lift it away from us. So our body warms up a layer of air right next to it, and then this air naturally rises away from you. Or even worse, if you're outside and it's a cold, windy day, the wind is blowing air that hasn't even been warmed yet by your body right into you, right? And that's actually why, that's what wind chill is meant to try to capture, right? That's why the outdoors feels so cold on a windy day. Your body is losing heat a lot more rapidly because wind is bringing cold air and using that cold air to replace layers of air that's already been warmed by your body. Okay, so what can we do to limit or combat this kind of convective loss of heat? The fact that our bodies conduct heat to the air around it, and then that warm air rises away. Well, one evolutionary strategy is something that a lot of mammals have aplenty, which is to have a lot of hair or fur all over the body. And what's going on there? So fur, for instance, is like this dense tangle of fibers, right? And hair is also, I guess, a dense tangle of fibers that are right next to an animal's skin, right? And what that dense tangle of fibers is doing, so, if I have, for instance, a rabbit, I don't know how to draw a rabbit. Close enough? Close enough. I have a rabbit, and it's covered with fur, with this dense tangle of fur. It's looking a little better, I suppose. If I zoom in here, what that looks like is this dense crisscrossing tangle of fibers, hair fibers. And what that's doing is trapping little pockets of air next to the rabbit's skin, right? So what happens is that the skin of the rabbit's skin, warms this air up. And then the tangle of hair or fur makes it a lot harder for that air to get convected away. It experiences more viscous forces, and so it tends to stay close to the skin for longer than it would have if there wasn't any of this hair or fur, right? So the rabbit's warm skin then is surrounded by this jumble of fur and trapped air, and both fur and air itself conduct heat really poorly. And since the air isn't getting convected away, the rabbit can stay, pretty warm in the wintertime. And that's basically the strategy that lets animals survive in the Arctic or during the wintertime or things like that. They slow down convective heat loss by the composition of, their hair or their fur to such an extent that they can maintain their core body temperatures, right? You've probably noticed that humans, we've evolutionarily lost the overwhelming majority of the hair that we once had. And so instead of wearing fur, we wear clothes. We use clothes, right? And the insulating function of clothes is that just like the fur on a mammal, they can trap air close to our bodies, right? So we put on a nice coat. That puffy coat has layers of cloth fibers and stuff like that traps air, stops it from flowing away from our bodies, reducing this kind of convective heat loss. Actually, that same idea is also used in wetsuits if you've ever been swimming in very cold water. The way a wetsuit works is, it's this weird spongy material that traps water next to our skins. And so once our body warms up the layer of water in the wetsuit, that water then doesn't flow away very easily into the rest of the ocean. And so we keep this layer of pre-warmed water next to our skins, limiting the convective heat loss. In that case, where the fluid's not air, it's water. It's kind of fun. Okay, the final mechanism that we have to talk about is radiative heat loss. So limiting heat loss to radiation. So as we mentioned above, any object is actually constantly emitting and absorbing electromagnetic radiation, right? These electromagnetic waves. And the amount of thermal energy that any object is radiating away per unit time, so the amount of energy per unit time, that's the thermal power that it's radiating away, can be expressed by something called the Stefan-Boltzmann Law. And what does this law say? Let me write out the equation for it first, and then piece by piece we'll walk through it. It says the power that an object radiates away is equal to some factor, E, which we'll call the emissivity of the object, multiplied by some constant, which I'll use the Greek letter sigma. So E multiplied by sigma. This is the so-called Stefan-Boltzmann constant, and I'll tell you the value in just a second. Multiplied by temperature to the fourth power. This is absolute temperature to the fourth power, multiplied by that object's surface area. Okay, so let's walk through each of these things in turn. P, well, that's just the thermal power radiated away by an object. Radiated by object. So whatever object you have, it's constantly emitting electromagnetic radiation, and this is the amount of power that's being emitted, the amount of that kind of thermal power via radiation. E, this is the emissivity. This is the emissivity of an object, and it's a property, depends on surface of object. E ranges, this emissivity ranges from 0 to 1. So in this equation, E is always going to be a number that's in between 0 and 1. Okay. Now, because it turns out emissivity is also related to how well objects absorb incoming radiation. And, as humans, we perceive objects that absorb all incoming light as the color black. And so things that have an emissivity of 1 are sometimes called ideal black bodies. Ideal black bodies. Again, because objects appear black when they're absorbing all visible light. And so if something is at the range where it's most efficient at emitting and also most able to absorb incoming electromagnetic radiation, we might call it an ideal black body. The opposite end of this is when the emissivity is 0. There's no fun name for that, unfortunately. But 0 are objects, let's say, that reflect all incoming light. And so in the visible part of the spectrum, objects that reflect all incoming light appear as if they're white. And objects that reflect all incoming light throughout the spectrum often have a kind of shiny appearance to them. And so low emissivity things tend to be shiny metals, for instance. Okay, so that's power, that's emissivity. Sigma is just a constant that makes this equation an actual equation. And in the SI system of units, this is 5.67 times 10 to the minus 8, and it has units of joules per second per meter squared per Kelvin to the 4th. And you can kind of see why it has to have this collection of units. Remember that power, this is 1 watt, which is 1 joule per second. That would be the units of power. And emissivity, this is just a number, a pure dimensionless number between 0 and 1. So to get the units to work out, I have joules per second on the left. And on the right, I'm going to have something multiplied by 4 powers of temperature and 2 powers of length. So the units of the Stefan-Boltzmann constant are joules per second divided by 4 powers of temperature divided by 2 powers of length. You don't have to memorize any of these constants, but I'll point out that the Stefan-Boltzmann constant is particularly easy to memorize because it's 567 times 10 to the minus 8. It's one of the beautiful things about the SI system of units. Anyway, it's just some number. The temperature is the absolute temperature of the object, right? Absolute temperature of object. So when you're using this equation, because temperature has to be written as an absolute temperature, we basically always use the Kelvin scale, something where 0 really means 0 temperature, 0 thermal energy. And then the last piece of this, A, is just the surface area of the object. Okay. So, great. So that's how much power an object radiates away. And actually, one of the points that I want to make is that, the thing that we probably have the least intuition for is this emissivity. An object that appears really black, well, that's black in the visible part of the spectrum, at least when we're talking about how it appears to human eyes, right? But the whole electromagnetic spectrum is a lot more than just visible light. And so sometimes we can be deceived when we think what color is something in the visible part of the spectrum, because the emissivity in this formula really refers to kind of its typical emissivity over the entire range of electromagnetic, different electromagnetic waves. So actually, the emissivity for human skin, even my skin underneath this shirt where I have a terrible farmer's tan, is still actually surprisingly high. You might have surprisingly close to 1, that is. Surprisingly close to as much of an ideal black body as it could possibly be. For human skin, even pretty light human skin, it's 0.97, right? That's great. The things, again, that have low emissivity tend to be things like shiny metals, right? Things like aluminum foil or, gold or things like that. Okay, so I want to say a few words here when it comes to, now that we know this is an equation for how much power we're losing to thermal radiation, what does this tell us? First, notice that factor of T T to the power of 4, right? Absolute temperature to the power of 4. This is a factor which grows really quickly. And actually, that explains why radiative heat transfer can be so important, right? When we feel the radiated heat of a fire, the difference in temperature between the fire and us can be quite large. The amount of heat flow by direct conduction through the air, right? That's only proportional to the difference in temperature between us and the fire. But for radiative heat transfer, the fire is radiating T to the power of 4, and that's a lot bigger, right? So that's why we feel the radiated heat from a fire, even if the air in between us and the fire is still quite cold. It also explains why the sun hitting us, we can actually feel that warmth. Even though the sun is incredibly far away, it's very hot, and very hot to the power of 4 is a big number. The sun puts out an enormous amount of thermal radiation. Right? Just to give you a random sense of scale, let's plug in typical numbers for a person. How much power is a typical human always constantly radiating away? Right? So the emissivity I just said was something like 0.97. The Stefan-Boltzmann constant, that's 567 10 to the minus 8. Joules per second per Kelvin to the 4th per meter squared. Human body temperature in Kelvin, not human body temperature in the core, but actually just at the surface of our skin, because that's going to control how much we actually radiate away. I looked this up. This is about 306 Kelvin. Need to raise that to the power of 4. And then the typical surface area for a random adult human. Anyway, it's something in the ballpark of 1.6 meters squared. This is kind of for a person on the smaller side of things, I suppose. Plug in all of those numbers, and that's about 772 watts, right? So if you were to suddenly find yourself in the vacuum of space with nothing warming you up, even if there was nothing physically in contact with you to conduct heat away or to convect heat away, you would still be radiating thermal energy at almost 800 watts. And at that rate, you would get quite cold quite quickly. So the first thing that kind of helps us from freezing to death when we're standing on the Earth is that, yes, we really are radiating all of this power away constantly, but we're also constantly absorbing radiated power, radiated thermal energy from other stuff around us, right? So the Earth has some temperature, and we get thermal radiation from the ground, so on and so forth. So that's great. There's not much we can do to prevent ourselves from radiating out this power, but we're constantly receiving power too. And there's also a lot that we can do to kind of prevent ourselves from losing the thermal energy that we are radiating away using insulation, right? So for instance, if we have a heavy coat that's next to our body is radiating heat, and a good portion of that heat that we're radiating away can be absorbed by the material in the coat itself. And so that goes into warming up the coat, which is right next to us, which will help keep us warm in the first place. As long as the coat is a poor conductor, which is to say a good insulator, right? Another thing that we can do is play around with the emissivity, right? So if we're just standing, just with human skin, the emissivity is pretty high. But what if we wrapped ourselves in something that had low emissivity, like wrapped ourselves with metallic clothing, shiny metallic clothing, where the emissivity can be a lot lower, right? So, what would happen there? Our body would radiate, would emit thermal radiation, and then the shiny metal wouldn't absorb any of that radiation. It would just reflect it right back to us. And so we could stay pretty warm. This is actually the same principle behind wrapping food in aluminum foil, right? So on the one hand, say you've just wrapped a piece of hot food in aluminum foil. Aluminum is a really good conductor. And so, the food starts to lose a lot of heat by being conducted through the foil and then to the air next to the foil. On the other hand, that shiny aluminum foil will reflect all of the thermal radiation that the food is trying to give off, right? Reflect the thermal radiation from the food right back at the food, keeping the food warmer for really quite a lot longer. That's also why emergency rescue blankets are made out of metallic cloths. If you wrap yourself in a metallic cloth blanket, it stops you from exchanging thermal radiation with the rest of the world. You radiate, EM waves, but they just get bounced right back at you, so on and so forth. Just as a quick comment, transparent windows, so let me just say low emissivity things like I said above, are like shiny metals are a canonical example. Shiny metals. Also, though, transparent things are low emissivity. But they're low emissivity in a different way, right? So transparent objects are typically transparent only over some part of the electromagnetic spectrum, but let's leave that kind of detail aside for the moment. A shiny material doesn't absorb electromagnetic rays because it reflects them. So there's a shiny, aluminum foil, there's an incoming bit of thermal radiation, and it just bounces off. In contrast, transparent materials don't absorb that radiation, but it just lets it right through, right? And you've probably noticed that when sunlight is like streaming through a window onto a patch of floor, and you have like a warm spot on your floor, because the window hasn't absorbed very much of the thermal radiation, you get a warm floor even when the window itself is staying cool. All right, so those are kind of ways of thinking about, well, given these three types of ways heat can flow, what are the physical principles we can use to understand the quantitative details of that heat flow? Certainly very quantitative in the cases of conduction or radiation. And given those mechanisms and those quantitative understandings, we can start to think, well, how does insulation work? How can we better insulate and stop, say, a building from losing heat to the outside world during the winter, or stop us from constantly needing to run air conditioning during the summer, right? Insulation works both ways. And in the homework sets, we'll think a lot more about using each of these physical mechanisms to think about how, say, we insulate a house and stop heat flow and, help save the environment.